Hello. In this video, we want to find all values of x where the following piecewise defined function is discontinuous. To do this, first we want to look at f of x. Well, the function is f of x is equal to the piecewise defined function of x plus 1 when x is less than 1, x squared minus 3x plus 4 when 1 is less than or equal to x is less than or equal to 3, and 5 minus x when x is greater than 3. Okay, so first of all, notice that any of these are just all of those are just polynomials, right? So because of that, these are just defined, these are just continuous everywhere. So wherever these are defined in those regions, this function is continuous. It's only at the edges of those regions could this be discontinuous. Now the question is how and why would they be? Well, if we're going to graph this here in a little bit on the calculator so that you can see this. But what I need to do is look at these edges. Notice that x is less than 1 here. This is where x is greater than 1 and less than 3 at the same time. And this is when x is greater than 3. So 1 and 3 are the only two possible values of x where this could be discontinuous. So what I want to do is I want to know what is the limit as x, well, sorry, one second. We want to go through the three things that we need. Remember, the first thing we need is that the function value exists. The second one is that the limit as x approaches k of the function exists. And we want the last one to be where the limit as x approaches k of the function value is equal to the function value at k. So we want to go through these. At x equals 1 is the first thing we want to look at. Okay, so what I want to know is what is f of 1? Well, to figure out where we plug this into, notice that we want to test these. Is 1 less than 1? No, it's not. So this is not true, which means I don't use this definition for f of 1. Coming down here, ignore the 3, just looking at the 1. Is 1 less than or equal to 1? And the answer is yes, it is. So that's true, which means that this is what we're going to plug this into. So plugging this in, that gives us 1 squared minus 3 times 1 plus 4. And then simplify. 1 squared is 1, negative 3. So 1 minus 3 is negative 2, plus 4 is 2. So f of 1 is equal to 2. Good. That was the first condition. Next, let's look at the second condition. The second condition is to determine if the limit exists. But to figure that out, we're going to have to ask, what is the limit on each side of 1, to the left of 1 and to the right of 1? So we want to know what is the limit as x approaches 1 from the left of f of x. Now, if you're to the left of 1, let's say you're at 0. Is 0 less than 1? Yes, so this is actually the definition you need. Notice if we plug it in here, is 1 less than or equal to 0? No, it's not. So we wouldn't actually use that definition. Same thing down here. Is 0 greater than 3? No, it's not. So I wouldn't use that. I would only use the x plus 1 here. So to determine this, we simply replace f of x with x plus 1. Now, it doesn't matter if we're going from the left or the right. We're just going to replace the x with 1 here because this is just a polynomial. And that's going to give us 2. So the limit as x approaches 1 from the left of this function is 2. The next thing we need to do is figure out the limit as x approaches 1 from the right of f of x. In other words, just to the right of 1, what is the function value? Well, notice that if I go right of 1, let's say even just 1.1 would work. Is 1.1 less than 1? Well, no, it's not. Is 1 less than or equal to 1.1? Yes, it is, and that would work. So we would actually use this in place of f of x there. So this would be the same thing as the limit as x approaches 1 from the right of x squared minus 3x plus 4. And then you just plug in 1. So 1 squared minus 3 times 1 plus 4, that will give us 2. So notice that that is also 2. Now notice that the limit here from the left is the limit here from the right. They're the same value, therefore the limit exists. Good. So we just determined that that second condition works. Now let's look at the third condition. Notice that the limit as x approaches 1 of f of x is 2. We know that f of 1 is 2. Therefore, the limit as x approaches 1 of f of x is, in fact, f of 1 because they're both 2. And that is that third condition. Therefore, x equaling 1 is continuous. Because all three of these have been satisfied. Awesome. The only other place where this might be discontinuous is at x equals 3. So let's see how that works. So at x equals 3, the first thing we do is make sure that's actually horizontal. There we go. So f of 3. Notice if I plug in 3, 3 less than or equal to 3. Yes, it is. So I need to actually use this condition. Notice if I do 3 greater than 3, that's not true, so I can't use that. So what I would actually use this for my definition here. So that's going to give me 3 squared minus 3 times 3 plus 4. And then simplify. 3 squared is 9. Negative 3 times 3 is negative 9, so those cancel, and we're left with 4. Which tells me f of 3 equals 4, and that also tells me that f of k exists here. The second condition is that the limit as x approaches k of the function exists. So we need to look at the two different limits. So the limit as x approaches 3 from the left for the function, and that's going to be here, and we're going to use this definition. So that would be the limit as x approaches 3 from the left of x squared minus 3x plus 4. Notice that you can just plug in the 3, and that's actually going to give you the 4 here. Good. So the limit as x approaches 3 from the left is 4. The next thing we want to do is look at the limit as x approaches 3 from the right-hand side. Well, that would be the limit as x approaches 3 from the right. But if we're to the right of 3, that means we're greater than 3, which means we're in this region. In other words, think of 3.1 or maybe 4 or something like that. So 4 greater than 3, yes, which means we use this definition of 5 minus x. So that'd be of 5 minus x here. And then just plug in 3. 5 minus 3 is 2. So there you go. But notice that the limit as x approaches 3 from the left of f of x equals 4, and the limit as x approaches 3 from the right of f of x equals 2. These are not the same thing. This isn't approaching the same thing on either side. So therefore, that'll be easier to see there. Yeah. So therefore, you have to say that the limit does not exist. So therefore, the limit as x approaches 3 for the function f of x does not exist, D&E. Which means that because of this second condition, at x equals 3, it is discontinuous. And this is the only place where this is discontinuous, because everywhere else, it was guaranteed to be continuous because it was polynomial. Alrighty, here's all the work that we just did. It was quite a bit, but we're not quite done with this. I want to go ahead and go to the calculator so that you can kind of see what's happening if you want to use the calculator to help you. Alrighty, I'm going to go ahead and I will see you there. Hello. We're Okay, so here we are at the calculator. Let's go ahead and go into y equals. Let me go ahead and, whatever. Let's go ahead on y1. We're going to type in all of these definitions. So the first thing we're going to do is open in parentheses. And then type in the definition that we had, which is x plus 1, and close parentheses. Open a new parentheses and type in that domain that we saw there, which is x is less than 1. Now to do that, you don't start with the x. That's not what we need. Press second math and then go to conditions. We want x, and it's just less than, so it's that second condition. So x is less than, and now we want just the number 1. Close parentheses. And then plus, and then open a new parentheses and write down that second definition, which was the x squared minus 3x plus 4. Close parentheses. Now open a new parentheses, do second math, which is test, and then go to conditions. Now in these conditions, we had a dual condition where we wanted to be, it said 1 is less than or equal to x is less than or equal to 3. Now notice that this is actually written in this order. It's written this way for a reason. We want to use less than or equal to for both of these. So a number less than or equal to x and an x is less than or equal to a number. That's what we want, that number 5 there. But we need to make sure that we type in these extra things. So let's do second insert or second delete so we don't actually delete this. And the number that we had there was 1. Awesome. So you see the 1 is less than or equal to x, and then the and then x less than or equal to 3. Close parentheses. Awesome. Next, plus and then parentheses, and our next condition is 5 minus x, close parentheses. Open a new one, go to second math, which is test, write 2 to conditions, and then type in the last condition that we had, which was x is greater than 3, which is just this fourth condition here. And then 3 there, close parentheses. Awesome. And this should be the graph of this function. So set zoom 6, and there you go. Now notice that the only 2 places where we could possibly have a discontinuity is at x equaling 1 and x equaling 3. So at 1 and 3, you can kind of see what's happening. Let's zoom in to see if it works a little bit better here. There we go. Let's change the window. Let's go 0 to 5. And then negative 2.5 is fine. Yeah, negative 2.5 is fine. Let's go to max to be 3. Still not enough. Let's go max to be 4. No, still not enough. 4.5. Okay, good deal. So over here you see the line. This just continues going that way. But notice that x equaling 1, the line actually connects to the quadratic portion here. So it's actually continuous at that point. You don't have to pick up your pencil or anything like that. And then you just keep going to the quadratic here. And then at this point, it actually jumps down to down here, which is the line going down this way, which is the reason why this is discontinuous. Now notice that the function value is defined as this value up here. We don't see the open circle, closed circle, but there, if I was to give you a graph here, you would see a closed circle here and an open circle here. But notice that the function value exists, but the limit itself does not exist, because the limit from the left is 4, the limit from the right is 2. So those 2 limits are different. So there you go. Hopefully that kind of helps you understand why we just did what we did and why it actually really does help us with understanding continuity. And hopefully this will help you with being able to graph piecewise defined functions. It's really not that tough. It's just that this portion, the first parentheses, should be the definition that you see in the first one there, and then that second parentheses is the actual condition that you see, that condition where x is less than a number, x is greater than a number, or x is between two numbers. And then just keep going with that. Plus, and then, oh yeah, and don't forget the plus. It's very important. Alrighty. Well, I believe that's it for this video. I'm going to go ahead and end it here, and I will see you in the next one. Have fun.